Associate Professor Benjamin van Durme. I hope I pronounced your name well. The last word, please correct me if not. He's an Associate Professor at Computer Science in Johns Hopkins and a researcher at Microsoft Semantic Machines. And without further ado, I leave it to you, Ben.
All right, thank you very much. Yeah, so I'm Ben van Durme from Johns Hopkins Center for Language and Speech Processing, as well as Microsoft Semantic Machines, but this is work done at Johns Hopkins with my collaborators, Andrew Blair-Stanek and Nils Holzenberger. Okay. Andrew is a full professor at the University of Maryland School of Law. Both of my collaborators are PhD students studying at CLSP. Nils is soon to be on the market for those paying attention to those things. Okay, so broadly, natural legal language processing is a big topic. It's been going on for many decades. I'm not going to give a survey of everything under the sun for NLP. This is going to be a narrow talk on some things we've been doing the last couple of years. But there's lots of people doing lots of different kinds of things with legal language. In my case, back in the 90s, I was mostly doing projects in symbolic AI, so the tail end of that era. And I really liked the idea of like symbol pushing, and the fact that there was something maybe related to law and symbolic AI seemed really exciting. And then for various reasons, I put that down, moved more into natural language processing, question answering, dialogue. But while a graduate student, I thought, maybe I made a mistake. Maybe I shouldn't even be a computer scientist. Maybe I should just go to law school. So I was filling out applications for law school late into the night, rather than programming something I probably should have been programming. And then at the last minute, decided not to do it. But a couple of years later, some friends and I from grad school did have a bit of a startup on e-discovery. And we had actually a little bit of a prototype of something that actually connected to a company. And then for various reasons, we put that aside. And then I spent a while doing various things in computational semantics over the last 15, 18 years, until 2019, when a professor from down the street came into my office, where every spring, if you're a professor, there's PhD admissions, and various people come into the office and you ask them one by one, what do you want to do in your PhD? Okay, so that's the standard question. And Andrew, who was dressed almost as nice as this when he came in to visit for his interview, says, I want to use computers to find loopholes in tax law proposals. I said, well, that's very specific. And it turns out that Andrew had done an undergraduate degree in computer science and spent time as a developer at Microsoft before then leaving to do that JD. So he actually did leave computer science and became a lawyer, and then became a full tenured professor, publishing lots of works on federal tax law. And he decided in the next stage of his career, based on his rough knowledge of how NLP seemed to work and more fundamental knowledge of computer science and the law, it seemed like maybe this was something that could be brought to his day-to-day. So I said, cool. And a senior student of mine who we'd been doing a lot of thinking about language and logical reasoning jumps in. He says, yes, very cool. I like this topic a lot. Right. So statutory reasoning. Right. So there's books, there's a bunch of statutes. What are statutes? Right. These are just policies, laws, rules, and they just sort of describe what's true. I like statutory reasoning. I like these statutes. I like these laws because there's something sort of nice about the idea that they are completely artificial. Right. So it's not like natural science. Like there's just a nice talk by my friend and colleague, Hung Ji, on various things we can do about reasoning about the natural world, right? About chemistry and drug discovery and so on. Law is interesting in that we completely make it up, right? There's nothing about the natural world that says that a law needs to be true or false. It's that human beings decide socially amongst themselves that we're going to write something down, okay? And then given some case of real facts, so like real things happen in the real world, but then we have to decide whether or not these rules apply, right? And so sometimes there's a lot of similar cases that we can reason from. Sometimes we can treat this like a data-driven exercise. Right? So there's lots of cases that may all be related to each other that were all decided in some brief period of time. And this can literally be called case-based reasoning, going back decades into the symbolic AI days. Okay, but what if there are no previous cases that you can work from? Okay, so if you think about semantics, this is the cool part. This is why I'm very interested in this particular task, because for some domains, some very natural and very consequential domains, like the US federal tax law, the number of publicly decided consequential cases each year may be limited. Now, what does that mean? Well, that means that you could have big corporations. There's only so many big, giant, large multinational corporations, right? And they're big. They have lots of money, so they can afford lots of lawyers, and they can afford lots of accountants. And so every year, they're going to do their best to pay their legal required minimum amount of taxes. And the IRS and Congress might say, we think that you owe more money. And then they go back and forth about this. And in many cases, whatever is decided ends up being not in public, right? So you go in front of some judge, or you're going back and forth just with the IRS, and the accountants are sending information back and forth. And then they decide, the IRS decides, the company's right. The company under the current laws doesn't owe the taxes that we wish they owed. It's a loophole. And so they change policy as a result of these cases. All right, so you don't have many of these cases because you don't have that many companies. And as a result of these cases, the law mutates. So this is a very natural problem. Like, it's a real world problem where there is no large collection of examples tied to a static set of rules. You have relatively few cases, and the law mutates often as a result of each case. Okay, it's a whack-a-mole adversarial system where the IRS is trying to change policy around very clever lawyers and accountants. Okay, but it's a big deal thing for society because we're talking about billions of dollars in taxes that may or may not be paid that could fund all sorts of social services. Okay, so if there's no examples, then how do you go about doing this? Well, you have to build systems that actually understand the statutory language. Okay. So we may have previous versions of the law, right? So these statutes change over time, but we do know what the statutes were at some point, and we know a particular case that was decided one way or the other based on these statutes. And so we now have a very natural setting where we have one or two shots at a time, where I'm going to pair a case with a set of statutes, and I know how it was decided. But then tomorrow I might write new policy. I might have new statutes. And so there's no case yet that's been decided. So when some new set of facts emerge, I have to decide on the fly for these statutes, for which I've never made a decision before, how do I interpret these laws with respect to these cases? Okay, so we need to learn how to break down these complex systems of rules, how to reason with them for a given case, and how to generalize these rules beyond training time into test time prediction. Okay, so there's further discussion of this by my student, Nils Holzenberger, on an NLP podcast hosted by AI2. But for the rest of this talk, I'm going to discuss iterations on formulating this computational statutory reasoning task. Okay, so first off, was a presentation last year at a different workshop at KDD. Okay, data set for statutory reasoning and tax entailment and question answering, where at the core of our work in this topic has been this data set that we call SARA. It's a statutory reasoning assessment. And this was a lot of work, largely by Nils, who manually went through US federal tax law and selected 9 sections of law by hand and pruned and edited this. So sections of law all have cross connections to other sections. It's a big graph. So you found a bit of a locally connected component and kind of pruned away the writing to slim this down to a set of 9 stylized sections of federal law. And then manually wrote 376 cases, 376 synthetic case descriptions, covering each of the different subsections in the tax computations that are covered by these 9 sections of law in SARA. And then critically, Andrew, who, in addition to being a PhD student, is a full professor who regularly publishes on issues of concerning the IRS on US federal tax law, vetted every one of these cases and the interpretations. Okay, so this is a very gold data set with respect to US federal tax law, synthetic, but high quality. Okay, so some features of SARA. At the core of the task that we're defining, it's going to be, does someone owe taxes and how much taxes do they owe? All right, so if you want to know how much taxes you owe, then you pull up statutes. Right? So these are the rules that define how much taxes that you owe. Okay, so SARA is full of text like this in terms of the statutes. And these statutes have hierarchical structure, so you have to learn to interpret language within a hierarchy. So rules with subrules with subrules. There's numerical reasoning. This is taxes, so there's definitely lots of numbers. So there's a lot of formulas written out in natural language embedded within these statutes. There's cross-references, as I mentioned before, where references to other sections can be either implicit or explicit. And you have to learn how to interpret the current statute with respect to the fact that it's now referencing some other big chunk of text in another location. There's some common sense where not all terms are necessarily technical terms, right? You need to know, like, what is a stepdaughter, what is a daughter, a stepson, a son. There's temporal reasoning, so you're reasoning over various months and years in these statutes. There's exceptions and substitutions. So not only do you need to interpret a running set of text that's hierarchical with all the things I just mentioned, but at some point as you're reading that statute, you could then have a clause that says, oh, by the way, if this one particular thing holds, then redo the interpretation of everything you just read. Okay, so that's a trick. And then there's even some conditional counterfactuals. Okay, so what do we mean by actually doing this task? Okay, so we have two different forms of problems. We have these binary entailment problems, and we have numeric questions. All right, so the binary are, does somebody owe tax, essentially? It's like, based on this case description, does this particular section or subsection apply to this case description? Yes or no? And then separately, how much tax does a particular person owe based on this case description? Okay, this is hard. This is very hard. Okay, this data set is designed to hopefully require real natural language understanding and logical reasoning. And to verify that the task is actually solvable, we also provide a full manual mapping to Prolog. Okay, so every statute has been manually translated into a set of predicates. And then the facts of every case is manually converted into knowledge graphs. Okay, so for example, here's a bit of a statute. And we have horn clauses associated with each of these statutes. Okay, so this particular subsection applies. That's the top of the head of the horn clause, if various other things are true as defined inside the text of the statute. Translating facts of a case. Okay, this is a very sort of simple, interpretable, logical form. Okay, so can we automatically solve these questions? Well, the Prolog solver, by design, achieves 100% accuracy on the task. Okay, so if we could perfectly map the statutes to an appropriate structured representation and perfectly map the case descriptions to a similar representation, then we can solve everything at 100% accuracy. However, off-the-shelf ML solutions perform near chance on this data set. Okay, SARA is purposefully sparse, so there's only 376 examples. There's not very many examples, especially for tasks as complex as this. When I say purposely sparse, I mean it was very tedious to put this data set together. It's a lot of effort. And the only sort of people that could really vet if this data is correct would be lawyers, right? This would require a lawyer to sort of authorize or sanction this data set. And it turns out you have to pay lawyers money, and they're not cheap. So it's not an easy thing to just go build a lot of synthetic examples. And as said at the beginning of the talk, this is under this problem, there aren't lots of cases. Just naturally, there aren't very many cases that appear. Okay, that's the whole point. Right, so this is like a real world problem that we really don't have a great idea on how we would generate huge amounts of data to augment, at least not off the bat. Okay, so the recent agenda has been iterating on this data set in various ways. Think of what are different kinds of approaches people have been taking in the community in terms of natural language understanding, and how do they apply to this problem. Okay, so for example, this Boolean question of does a particular section, a particular case description, is it valid to say that a particular section of federal tax law applies to that context, to that case description? Okay, so this seems very much like a RTE kind of model that we might apply. A lot more complicated text, a lot larger context, but we might be able to just optimistically, maybe we can just take this data and pipe it through a pre-trained NLI model and something will happen. I'm not going to get much into the details about the numerical reasoning portion here in this talk, but we can maybe we could just treat this as basic supervised regression. In particular, we're aiming to predict roughly how much taxes someone might owe. Okay, so here's a bunch of numbers, and there's various things at the bottom. There's a y-axis on the left and there's a y-axis on the right. Don't stare at this very much because this is effectively a chance. Okay. Right. So the contribution of this paper was the data set. This is a data set paper. And then we applied a number of pretty reasonable baselines, off-the-shelf types of models that just didn't work at all. Okay, so in order to keep ourselves honest, so we don't want to just say, oh, this is hard, this is impossible, we can't, no one can do this task, we promise. Rather than taking entirely off-the-shelf models, we say, well, these models are based on sort of off-the-shelf encoders like a web text-based BERT, and that maybe that's not fair. Right? So maybe we need to at least adapt the underlying encoders in order to have better pre-training before going into this task. So we've done various projects on this, like training various kinds of text vectors for purposes I won't get into here, and then legal BERT. Right? So there's a project out of Harvard called Case Law. Right? So case.law provides millions of cases. This is a massive archive of publicly available federally cited cases. Okay. Where we take BERT and grab every case from case.law that happened in 1970 or onwards, that have at least 400 tokens, and a little bit of filtering leads to roughly 1 billion tokens of text for very significant continued training. Right? So 1 billion tokens that's enough to train a model from scratch. So we continue to train, and then we invent our own intrinsic task, right, to verify that there's something going on in this legal adapted version of BERT. So we've bought an actual physical book, and we had it scanned and OCR'd. So this is Black's Law Dictionary. So there's not freely digital versions of this book available, much like Hongji was saying that various serious places don't want to necessarily give their stuff away for free and let you publish on it. This is the case in the legal domain as well. So we can't just grab a machine readable version of this dictionary. So we built our own. And then we created a task called legal term recognition. So given a case description, we want to be able to predict whether or not a particular phrase, particular span of text inside that case description is or is not something we would consider a legal term of art. I'm not going to get more into the details here, other than it's a relatively simple sequence tagging task. And the point was only that a BERT-based model did significantly worse than a model that had access to the legal BERT encoder. Right? So it was much more in domain. And it turned out to be better than Andrew himself at the task, as well as a colleague. Right? So it was better than lawyers at being able to recognize these terms. Okay, so the point is only it's a real thing. Like it seems like this language model now has a pretty good idea of what legal text looks like, and most importantly, the perplexity of legal BERT on the descriptions from SARA is significantly lower than off-the-shelf BERT. Okay, so we very much have like a legal adapted model. And so here's some more bar charts. Again, a couple different y-axes. Doesn't really matter much what this says because they didn't help much. Okay, so we had the point is we have intrinsic measures and like in side tasks for legal information extraction, and verified that our underlying coders definitely know something about the law. They know at least the relative distributional statistics of legal language, but swapping those encoders in for an sort of contemporary style of recognizing textual entailment sort of model doesn't allow us to just magically read all these statutes and case descriptions and pump out an answer in one end-to-end shot. Okay, so statutory reasoning. So as said, manual NLU in the Prolog solver is sufficient. So if we can perfectly map everything over to structured form, then we know we can get this right. But off-the-shelf and domain-adapted machine reading models struggle. Right? And when we do some ablation experiments, it suggests that based on such a limited amount of training data, the statutes are essentially being ignored. Right? So there's just such, I mean, they're big, they're complicated, and based on a tiny number of examples, which are moving from the they're moving from subsection to subsection of these statutes, right? So you're not even seeing even a few training examples for a particular statute, right? So each of these examples are moving across the statutes. And the model is just has no idea what to do with this, which is what we expected, but we spent a fair amount of work to verify that that was the case. And so what could we do? Well, since we know that the manual solution, the manual NLU solution works, then we could try to replicate that. Like maybe we could go all in on legal semantic parsing. Maybe we could do some new science and efficiently creating a lot more data. So I say that SARA is sparse. Maybe there's ways that we can make it not sparse. Or maybe we can make the machine reading models more data efficient. So if we can't generate more data, then maybe we could somehow create new machine reading algorithms. And that was sort of the point of putting this data set together. And finally, maybe we can break this task into smaller individual parts that we can then optimize individually. Okay, so with that, I'm going to talk about a paper that Nils presented a couple weeks ago at ACL, okay, which is exactly trying to take this problem and factorizing it into a number of different subparts, where each of these subparts are recognizable tasks within the computational linguistics community. All right, so rather than these sort of language in, answer out models, right, like just like an end-to-end RTE style model, we're going to try to break this into subparts. And so we're going to first detect all of our arguments, or basically entity mentions for those in information extraction within the statutes. We're going to do coreference. And we do coreference between them. Excuse me, one moment. Forgive me. We're going to coreference across the arguments in the statutes. We're then going to convert those statutes into structured modules akin to neural modular networks. Okay, so we're going to find all the different places in the statute that might refer to some variable effectively, recognize which things are coreferent, and then we're going to build the structure up around those arguments to have interpretable modules. And then based on this library of inference modules, then given a particular case, we need to figure out how to apply these modules to the arguments from a case. Okay, so these first two components are very recognizable as legal information extraction. This is semantic parsing, and this is machine reading. Okay. All right, so argument identification. So in the statutes, we have concrete references. Right? So no matter what case a statute might apply to, the United States is the United States. That doesn't change. And then there's a number of case-specific values. Right? So for a given case, we're going to be talking about particular employees and particular people, perhaps particular contiguous countries to the United States. Right? So that changes on a case-by-case basis. Okay, so I'm showing some numbers only to be clear that the major point of this work is to break the task, the overall task, into a series of subtasks that we can do local optimization on and understand where we might be making errors. We have the BERT-based model here is reasonably sophisticated, but still we consider it a baseline. The point was, how doable are each of these individual tasks after doing more work on modifying the data set to support this task breakdown. Okay. So now doing coreference. So here we have a bit of a statute. Right? All these numbers refer to various coreference. Right? So for example, the taxpayer is referred to in a number of different ways throughout this statute. Whereas in other cases, like the taxable year, the taxable year, the taxable year, the taxable year, is all the exact same string. And this is by design, right? So there's, on the one hand, legal coref is a bit complicated in statutes because of the sort of structured nature and the cross-referencing across sections. So that's different from, say, newswire text. But on the other hand, some mentions are purposefully kept string identical or nearly string identical, right? In order to cut down on the amount of ambiguity. Right? No one wants their laws to be ambiguous. Right? And so here's some more numbers, just to say that we have a couple of baselines. One is just to say every mention is a singleton. And so there is no coreference, or just doing direct string matching. And these numbers reference when we have perfect argument identification. So if you have perfect mention spans, then coreference is at least the first 80% of the coreference is not that hard. That last bit is tricky. And when you put these together, then you end up with something a bit below 60%. Okay, so you're starting at the baseline a little under 60% before you start doing more sophisticated methods for legal coreference. And so we have some work ongoing on this. This is a collaboration with my student Patrick Shaw, as well as my other two collaborators, on sort of pushing forward on a more legitimate push on legal coreference. And one thing in particular that's interesting about legal coreference is the documents can be quite long, longer than most of the standard data sets that are used for coreference. And so we're building this work is building on something we presented last year that addresses this issue that the sort of standard mode for neural coreference blows up with long documents. And so the memory usage is linear in the length of the document, which then means that you simply can't process large documents until our work and a couple of other recent works that have been along similar lines. Okay, so back to SARA. So after we've identified each of the different arguments and performed coreference, then we want to discover the relationships between them. Okay, so we have this snippet of a statute that coreference has been performed on. At that point, we'd like to convert it into something like this prologue representation. Okay, so how are we going to do it? Well, one way we could do it is we could wish that there was a very tech-savvy Congress. Okay, so that every time that they passed legislation, or in the IRS wrote various kinds of policies, they would actually provide with it a canonical machine-readable form, right? And we're not nearly the first people to comment on that. There's been lots of people who have wished and dreamed that governments could codify their laws in a formally verifiable way, where then the natural language expression was merely more for human consumption, but that there's some technical logical form underneath of it was actually the definitive statements of the law. Okay, so we could pretend that that's the case, and that's what we're doing in this paper. So we propose no new work in structure prediction in order to derive statutes into Prologue, although I've done a fair bit of work in the last set of years in semantic parsing in some other domains. And so this is something that we're giving a lot of thought to here on pushing on this in the next couple of years. Okay, so what we're doing in this work, as we're seeing, we're assuming access to something that can do that final step of the structured prediction. And in our case, we take this prologue from the last work, the existing prologue rules, and we can end up with these sort of tree structures, these inference tree structures that are familiar if you follow the work in neural modular networks. Okay. So finally, the step that we call argument instantiation, this is the actual reasoning. So now that we have some structured representation of the statutes, we want to go ahead and actually do inference with them. And so how do we apply them to a case? So for this, we're going to extend some prior work that we presented last year on event extraction as definition comprehension. So what does that mean? I'm going to jump over to that briefly, where there's lots of data sets that are annotated according to annotation manuals. So organizations like the Linguistic Data Consortium gets together a group of people. They're professionals. They think very hard about something that they want to annotate, like an event corpus, where they're going to annotate a lot of examples, and they're going to provide those examples to computer scientists who are going to build models to automatically predict what was being annotated. And in the course of those annotations, they decide amongst each other how to write, how to write out the annotation guidelines. Right? And so historically, machines read the examples, humans read the definitions. And so our group's been thinking a lot in the last few years about how do we take those definitions and actually pipe them right into the model, because in these really low resource settings, it might be that we can't expect many or any examples of the actual things we're trying to predict, but we might actually have a description of what it is that we want from the user. So you have a definition like this, right? So some sort of die event. And there's various ways in which that event might manifest. And so what we proposed in that work There's a number of ways you could go about this, but in that work, we proposed that we would associate with each definition a set of what we refer to as semantically bleached statements. So this is sort of like a canonical statement that captures at least one of the versions of the event that's being defined in that definition. Okay, so annotators regularly provide examples in annotation manuals, and what we're suggesting here is just provide these bleached statements. These are the canonical statement of what you're after. Okay, so then if you want to actually perform information extraction, and I have like a piece of text here, and I say, well, that term sort of triggers one of my bleached statements. Okay, so now I have a standard sort of set of slots that I need to fill. What I can do is I can take this text of someone killed someone else with something in some place at some time, and I can say, I want to fill in that slot. Okay, so I'm going to query the text by interpreting this single sentence with a notion that I care about the encoding of this particular span called someone. Okay, I'm going to pipe that through a model in order to identify US troops. Okay, so this is very much like very akin to models that perform question answering, like something like the squad data set. Okay, so then you get US troops. So now once you get that value, you can put that directly into your initial statement. So now you have a slightly less bleached statement. So now we're committed to the fact that US troops killed someone else with something in some place at some time. So now I'm going to say, no, I want to fill in that slot, and I re-encode that statement, and I get a new answer, and so on. Okay, so you iterate through multiple interpretations of this statement. So jumping back to SARA, okay, so we have these case descriptions, and we have input values. Like we're going to say that a particular variables need to be set. So we think that that Alice, we're concerned with Alice being the potential taxpayer, and 2017 being the potential year. And what we need to do is fill in a series of other variables. Okay, so the text description is below of the statute, and for which there's then this corresponding structured object that we talked about before. And we're going to do the same trick, although it's a little bit more complicated because now we have multiple references to that variable throughout the, potentially multiple references to that variable throughout the text. So you have to somehow aggregate the representation of these slots throughout all the different text. Okay, so we swap in Alice, and then we query on household, okay, and so on. Okay, we're going to fill in each of the different values. Each of these is this iterated question answering sort of task. Right, the text of the statute forming the bulk of a question is saying, here's a statute, and I want to fill in this particular coreferent variable, and then I want to fill in this coreferent variable. I want to fill in that coreferent variable. Okay, and now breaking up and out from one piece of a statute, we have these trees that we talked about before, where we're going to do this sort of bottom up. So we're going to fill in each of these different sections, right, with weighted truth values coming from the overall entailment score, coming from the resultant sentence with respect to the context or the passage of the statute, all the way up to the top. Okay, and so to train this, definitely wouldn't be possible with just 367 examples. So, here we perform data augmentation by sampling from all possible case statute pairs. So we do have the 376 example cases paired to statutes. But we have lots of statutes that we've coded up. So we can just take all possible statutes that we've coded, each of which are in Prolog, and where before we might only be asking for a particular case, a particular query with respect to a particular statute, like for this case, is it the case that Alice in the case description owes taxes according to a particular piece of the statute? And so we can ask for all the statutes for all the people in the cases, whether or not they owe taxes. And because we have previously defined a manually constructed knowledge graph for each of these cases, then we can actually use our Prolog solver to tell us the answer for each of these synthetically generated queries. So we can generate orders of magnitude more examples in order to initialize, pre-train these models. Okay, so here's again some numbers. The key thing here is that this is now better than chance performance, and the data augmentation helps. Right? That's the, but there's a lot left to go. So it's not worth delving into specific bits of details here, because this is nothing that you would bother shipping. This is nothing even you imagine asking your boss for more resources for to continue to work on. Right? This is we were very excited that it was non-random. Was the main result of this. And again, the main point of this work was to break the task up now into a series of individual modules that we can now attack with more serious research, like visit writing papers entirely dedicated to just one aspect of this overall problem. Okay, so the next steps on statutory reasoning for us. In particular with the numeric reasoning, which I didn't talk much about here, this is particularly challenging, and like prior work in other areas of numerical reasoning on language, we need to invest some effort into dedicated solvers. I'm particularly interested in this problem of sort of document level, long document level semantic parsing to be able to convert these rules directly into these interpretable modules. Generally better legal IE, so we need better coreference, better argument, mentioned finding, and so on. And of course, engaging with others that are interested in this challenge. Okay. So with that, I can take questions.
Thank you, Ben. Very exciting and challenging set of NLP problems. Questions?
Yeah, I have two basic questions. So first, if tax law has this data problem, why not picking another legal area to tackle where the examples are more? And the second question is, how do you make this useful for lawyers, especially when now you already break the problem into sub-problems, you can solve some of them. How do you imagine some of these sub-problems are useful for lawyers?
Okay, those are both great questions. So I think for the first one, I would say that is the like finding my keys and the searchlight, the lamplight problem, right? So like, sure, like I know how to solve problems when I have a lot of data, but yeah. The point is like, this is actually a real problem. Like it is the case that you write statutes and tomorrow there's facts and you need to decide, do the facts apply to the statutes? And so you either say, well, you know what, we only work on problems where there's lots of data. And so for the first 7 cases of the statute, then we're gonna have to ask a human all the time. But then in that setting, it would mean that we're always asking humans. Like we just have to give up on this problem because exactly because these statutes keep changing. We will never have lots of examples in order to reason from for the static set of rules. Like we have to learn to actually interpret those rules. And so a key goal here, going back to the beginning of the presentation with respect to Andrew wanting to get a PhD, what we'd really love, our dream with this work, is to be able to have a tool that you could provide to the IRS and Congress, that you could propose, you would basically prototype new legislation, new tax policy to say, before, rather than engaging in this adversarial effort where you write it and then companies come and then find loopholes, wouldn't it be better if we could just find the loopholes for you automatically ahead of time? So we actually want to be able to basically bang on proposed legislation to be able to find these problems right away. So as to your second question on how could these subparts help? Well, certainly we could say at least some of those subparts are applicable to lots of other areas of legal NLP, for which there's a robust community already, and so so there's at least crossover from that. More broadly, I think I'm hopeful that this line of work, even if not successful in the sense that it automatically finds all the loopholes and companies pay huge amounts of taxes, as a result. I'm hoping that before we get to that point, there's also educational benefits, that there could be, these are tools that would help people learning the law to work with it. So that I think even an imperfect, so I'm generally interested in this idea, not just in the legal domain, but generally with machine reasoning systems. I think there's a large potential that even if the system isn't right all the time, students working with such systems can effectively be tasked with, do you think the system made the right decision? And so they're basically working with a savant kind of machine student.
Thank you. Dave, please.
Hi. So interesting talk. I find myself having trouble thinking about your 300-ish examples. And I guess I, in particular, find, is there anything fundamental about the fact that they're in natural language? That is, it's not clear to me that anyone, whatever idealized tool you might eventually have, it's not clear to me that anyone would interact with that tool by writing little stories about the people, right? More likely you would have some graphical interface, or you'd be reading from a database. It's got the financial information. You pull it out of Intuit or whatever, or out of, you know, whatever gigantic companies use. So I guess, can you give me some sense of why bother to even encode these examples in natural language?
I see. So that's good intuition. That, yes, the real cases run long, and there is a fair amount of tabular data. But in the end, like the records are textual. I mean, you have tabular data amidst these documents, huge page after page after page of effectively scraped Excel spreadsheets that have been pasted in to these documents. But there's still a large amount of what needs to be reasoned with isn't just numbers, right? It is actual natural language descriptions of events, of some company acquired some other company, and in the act of acquiring this particular company, they decided that they were going to reincorporate in this particular island, and they did it on the very last day before something else happened, and then one officer at one company was hired by the other company right before it was acquired, and so on. And that there's a lot of a pretty large number of events that come to bear and are discussed in these statutes. It's not just a matter of calculating a few formulas. It's a lot of like complex descriptions of what might actually happen in the real world. So it's a mix. So I would say that broadly, yes. I think further iterating on a data set like this would involve bringing in more tabular data, which would then make the problem even harder, because now you have to do mixed tabular reasoning as well as text. But the text doesn't just go away. Like there is a significant amount of crucial information that can only be carried in natural language.
Okay, thank you.
Thanks, Dave. Alison?
Hi, I really enjoyed your talk. Thank you. I'm curious what your opinion is on how far you can really go with Prolog to represent legal reasoning. Like, do you think it would work for legal documents in any domain, or is there kind of a point at which it becomes a little too simplistic?
Yeah, I'm definitely not an expert in all areas of legal law right off the bat. So there's the huge qualification. There is a lot of ongoing work that's been going on for a long time at some sort of discrete formalized language for the law. So there's actually some researchers, I think, affiliated with Microsoft, if I have that right, with the French legal system, like trying to codify like the French legal code into like their own particular formally verifiable structured language, which to my very naive eyes, like I sort of skimmed this, it looks roughly like Prolog. I mean, it's some sort of like zoological language that you can reason with, but I can't tell you the differences between these. In particular, how they handle uncertainty, or if at all, how they handle uncertainty. In this last piece of work, we initialize the structured representation from the Prolog, but then train them so they can handle uncertainty. At the moment, that uncertainty is really all there because we're uncertain in the actual interpretation of the cases. Okay, so it's not that there's like ambiguity in the case descriptions and that we need to have uncertainty in the reasoning for that. It's because we just don't know if we did the alignment correct. And so different modules may or may not be able to be aligned very accurately. And so this the fuzziness of a neuromodule allows us to capture that. Getting into other areas of law, I don't know.
Thank you, Ben, and thanks, Alison. One last question that I piggyback here. In the spirit of breaking the problem into smaller modules, one of the sub-problem areas I'm wondering if it's a problem is that if you have a new case and you have basically these slotted filling templates for each of the statutes, is basically matching which one of the templates to start with in the beginning. Is it a problem at all? in any case?
I'm sorry, could you just restate that quickly? So is it the serial nature of the matching? Is that what you're...
Basically, if you have a new case, how do you decide which one of the statutes to start with in terms of the, which one is applicable?
I see. Yeah, so as the problem is currently formulated, the queries are with respect to particular subsections. And so what you would do in practice, like if this were actually a system that worked in this way, then you would say for this case description, for each subsection of each statute, do you owe taxes, do you owe taxes, do you owe taxes, do you owe taxes? So is there, which to some extent is how the system works. Is there any bit of statute that applies to my case such that I owe taxes or not?
I see. But still, there is actually some sort of retrieval or search that's going on at the statute level.
You would, yeah, if building this up, then you would need to have some sort of search procedure. I mean, I think for at least at the corporate level, this isn't the scenario that you would rely on sort of imperfect recall, right? You would want to know, like for those accountants and those lawyers are getting paid a lot of money to be sure that there is not a single line of any statute that applies to case description. So I think in some sense, you actually would want this full enumeration. You'd want to like linearly scan through all possible legal language that might apply to this case, taking a very broad interpretation of what might apply, and be sure that nothing applied.
Thanks again, Ben. Very informative and very challenging set of problems as you mentioned. So if there are any other questions, please reserve them for the panel on a set of related challenges. And we are